transmitters generate, and it can be high, medium, low frequency electrical energy. They are just generators of alternating current at the frequency you want. That's what the most basic radio transmitter is. It's radiated out an antenna as an electromagnetic wave, and we'll go into what that is in that section. And so the basis, the most fundamental basis of a radio transmitter is the oscillator. And the oscillator is telling you exactly what it does. It oscillates. So it actually generates that alternating current. And it hopefully generates it at the frequency you want it to generate it at. In amateur radio terms, that's called a carrier. It can carry other information. It can include other information. So, the most basic. Now I'll hand this around. This is that diagram on the screen. The most basic is we're using the Morse key to turn the oscillator on and off. That's all we're doing. And then the oscillator is connected to the antenna, which is included on the board as well. And we can, in the practical, we can listen for that signal if you just to prove that it is actually a transmitter, very low power transmitter. But that's the most fundamental. And this also gives you a bit of an idea. Some of the questions will have block diagrams like this, and some of them will have the words missing. And so it'll say, what is the block that is missing? And they'll have 4 options. Yeah. So, and we'll go into a couple of the examples of those. Now, we talked about a carrier. It can carry another signal, or it can be modulated with another signal. If we talk about voice, the radio term is radio telephony versus radio telegraphy, which is Morse code. If we superimpose voice frequencies, so those really low voice frequencies onto our really high carrier wave, we call it modulation. And if we superimpose those voice frequencies, and what happens to that radio wave is it goes up and down in size or amplitude, we call it amplitude modulation, because what your voice is doing is causing the wave to do this, increase and decrease in amplitude. Whereas, if our voice frequencies, what our voice frequencies are actually doing is changing the frequency, so it's just changing the frequency a little bit by however much your audio frequency is, your voice frequency is, we call that frequency modulation.
Can I ask a potentially stupid question?
Oh, okay.
Is voice just a shorthand for stuff humans can hear in that case? Is that what you mean by voice? So saying voice frequencies, is that just a shorthand way of referring to what humans can hear?
Well and truly.
Yeah,
it's the really low bit of the
so sometimes I'm frustrated literal and you're saying voice, I'm like, well, you could transmit music or like, so you mean...
Correct.
So
it's audio.
Yeah.
Audio frequency,
Yeah.
well and truly.
Yeah.
So it's the bit of the frequency spectrum right down the bottom. Just before DC. Just after DC.
So that's the audible stuff we can hear.
Well and truly.
Yeah.
Well and truly. And in fact, most of the digital modes that we use are based on audio frequencies, tones in audio frequencies. So this is a visual representation. And when I talk about amplitude modulation, so the top picture is very low frequency, and you can see it's really stretched out, so it's low frequency, versus your carrier wave, which is much higher frequency, and you'll see they're alternating much, much quicker. If we put those two together, one modulates the other, you end up with an amplitude modulated carrier wave. So the size of that wave is varying. As your voice goes up, you can see the amplitude modulation wave is going up as well. As your voice comes down, it's getting smaller. AM radio stations, your AM broadcast stations, this is what we're talking about. FM radio is, what happens is, as your voice goes up, you'll see the frequency modulated carrier wave they oscillate even faster, a little bit faster based on the size of your voice wave, and then it gets lower in frequency as your voice comes down. And so the key thing here is AM, you can see the power level is actually going up and down, versus FM staying exactly the same. So when you key down on an FM transmitter, you're getting the same power all the time. It's just the frequency that's varying. Whereas AM, it's based on the volume of your voice, the size of your voice. So that just keep that in the back of your mind. So, okay, here's a radio telephony transmitter. So we've got a microphone. We boost up that audio signal a little bit through an audio amplifier. We've got an oscillator that's supplying us with the frequency that we want. It goes through a thing called a modulator, which is a combiner, combines the two. Then we boost it up a little bit and send it out the antenna. So this is an AM transmitter. Now, we talk about single sideband. Single sideband is a mode that we use for voice, primarily voice. It's a mode, it's effectively a form, and for the foundation assessment, you need to know that it's a form of amplitude modulation. What we actually do is, though, we remove a lot of the, I suppose, what you'd call the superfluous information from that waveform, like the carrier and the sideband that we want. So, okay, there's a concept of when you add two frequencies together, you get the frequency added together, you get the frequency that is subtracted, and you get a whole lot of other harmonics as well. So, and that's the artifacts, I suppose, that you get when you combine two frequencies together. What we do in single sideband is we filter out the sideband we don't want, all of those bits of information that we don't want. So we've only got one side, and what we usually normally do is get rid of filter out the carrier as well, which is that center frequency. So it's a very efficient mode of transmitting information because it's only there when you talk, when there's something that's modulating it, so it's a very efficient mode, and it's also a very power efficient mode because you're only transmitting power when you're talking. When you're not talking, there's no power being transmitted. So yeah, it's single sideband. But the thing you need to know as a foundation license candidate is it is a form of amplitude modulation because the size of that signal goes up and down with your voice. Now, there's a whole lot of controls on a transmitter and receiver that you need to have a bit of an idea about. One of them is there's a microphone gain control. So this is the size of your voice signal. And a lot of people go, well, I can, transmit more power if I turn the microphone gain control up to 11. Okay. You're probably also creating a whole lot of interference and a whole lot of other bits and pieces. And people won't actually be able to understand you. That's the bottom line. So the microphone gain control is just the microphone volume level. We talk about foundation licensees having power limits of 10 watts on single sideband, and we talk about it being a peak envelope power of 10 watts. So if we go back to here, the output waveform over here goes up and down with your voice. Now, if you're looking at a power meter, and this is a external power meter, got a little meter on it, or some of them are built into the transmitter, and you go hello, hello, or you say your call sign or something, so you've got a bit of voice modulation there, and the power meter is telling you it sort of averages around about 10 watts. you're spot on. You're only putting out 10 watts of power, so you're within your license conditions. And that's why we talk about envelope power. It is within that envelope, it's around about 10 watts. Yeah, loudest volume should not cause the transmitter to exceed 10 watts. So that's why we call peak envelope power. Versus, if it's FM, as soon as you key down, you look at the power meter and it says 10 watts, spot on. If it's more than 10 watts, you need to back off the power control. And that's the difference between FM versus AM or single sideband. Now, in FM, of course, we call it something different. We call modulation something different. We call it deviation. So it's the amount that the frequency deviates. Now, there are limits which are specified by your class license, and you don't have to worry too much about this because the transmitter that you use will keep you within certain limits. But you think about it, if it deviates too much, it could actually take you outside the band. But your transmitter in most cases will keep you within the band. But you need to know that FM modulation is deviation. So that's a different way. If it's FM, it's deviation. AM modulation. Depends on the voice, volume. The more deviation, the greater the bandwidth, the amount of signal that it takes up in that radio frequency spectrum. If either AM or FM carriers are overmodulated, they can cause distorted output and then interfere to adjacent frequencies. This, as it says, could cause harmful interference too. In most cases, other amateurs, but in really severe cases, it could be out of band and causing it to other services or other users. Any questions? Go.
I was just wondering if that meant that AM was more common with people who built their own radios, because to get like a really good quality voice off an AM, you think it would just take a good power meter, which is kind of easy to build, but to get good FM, if you're trying to do like limited bandwidth, you need really good spectral resolution. Building that yourself is harder?
No.
No?
No.
Okay.
But there are homebrew FM and AM radios, well and truly. Yeah. And these days, like it can be all done in an IC or done in software for software-defined radios.
So does this mean that like there's kind of like a standard level of spectral resolution that you can assume that people's receivers are going to have when you transmit?
Well, that's actually defined. You need to have it within certain limits, and that's not only so you are understood, but also if you're using digital modes, those limits are actually more important.
Oh yeah.
So, which you'd know. So, yeah. Okay. So, now, do I go into this or do I not go into this? I'll go into it. Okay. This is a little bit of extra information. You really don't need to know this, but it just informs a concept that we introduce in a few slides' time. A crystal set. Now, this is a crystal set, and in fact, it's pretty close to what's on the diagram. This is what we call a circuit diagram or schematic, and don't be scared of it. You can see there's some of our symbols that we need to identify. So there's an antenna, there's an earth. Now, squiggly symbol, which is L, that's what we call an inductor. Now, an inductor is just a component that stores charge in a particular way. And a capacitor, which is these two lines, and this one's a variable capacitor, and this one's a fixed capacitor. This also stores charge. So, but it stores charge in a slightly different way to an inductor. And then we've got this funny symbol up here, which is called a diode. Now that's our detector, if you like. That's the thing that that rectifies or converts the radio signal and pulls out the audio signal for us. So we only get the audio signal out the other side. So that's really handy because we get rid of all that RF. This bit enables us to tune up the RF and tune to the station, whereas the D or the diode then pulls off the audio. So they're capacitors. They store electrical energy in a particular form. The inductors store that energy in another form, and what that means is in here it's what we call a resonant circuit. So it only receives at a particular frequency and enables us to, through that variable capacitor, tune to a particular frequency. So the concept that we're trying to get across here is it creates what we call a resonant circuit. And resonance, if you go on to standard and advanced, they go into this in a lot of detail. Resonance is a really special electrical condition, and thank goodness somebody discovered this, because this is what basically radio is all about. It enables us to tune to particular frequencies in both the transmitter and the receiver side, and the way that it works is the energy that is stored by that inductor and that capacitor sit there and go backwards and forwards through that circuit and enable us to then tune to that particular resonant frequency. Now, are we okay with that? And its resonance is the condition that I'm trying to get across here. It's really important because we now go over to receivers. Receivers are designed to select the required signal, so enable us to tune and then detect the modulation that it's designed for and boost it up, amplify it. So the role of a receiver is to do the reverse of a transmitter. Hopefully you get whatever went into the receiver at the transmitter at the other end, out the receiver at this end. And yeah, okay. So convert the modulated signal, so the RF and the audio, back to just audio. And it's called the detector. And typical, if it's FM, we call it something different, which is a discriminator. So you need to sort of know the concepts there. Now, I'll hand that round. That's honestly as simple as you get. How are we going for time? No, that's all right. So, if we move on from a crystal set, the next more complex receiver is what we call a tuned radio frequency receiver. Now, funnily enough, you'll notice that there's a couple of tuned circuits in here, which is one of these inductors and one of these capacitors in a couple of places. So what this is trying to do is, the signal that comes in your antenna, everything comes in your antenna. It's the whole frequency spectrum. But what you want to be able to do is just grab the little bit that you need, the little bit you want to actually receive. And so you've got a frequency selection circuit, which in this case they've represented as an inductor and a capacitor, a resonant circuit. We boost that up a little bit, so there's a radio frequency amplifier, boost it up. And then we've got, so what the first one does is bring us back to a particular part of the band. Then the second one gets us even further down. So it just receives the little bit of the spectrum that we want to receive. Otherwise, and one of the characteristics of early crystal sets was, if it wasn't terribly what we call selective, you could plug your headphones in and you could hear multiple radio stations at the same time. because it wasn't very selective. It was quite broad. And that's one of the characteristics of early crystal sets. There weren't too many of these frequency selection circuits. Then there's a detector. Now the detector, all that does is pull off the audio, ditch the RF, pull off the audio, boost it up a little bit, comes out a speaker or a set of headphones. 3 things you need to be aware of for receiver sensitivity, for receivers. Sensitivity, which is the ability to receive really weak signals. The selectivity, which is exactly what we're talking about, the ability to actually only receive or select the frequencies you're looking for. And then stability. Now, stability these days is probably not as big a problem, but when you had valve equipment, old valve equipment and that sort of thing, you used to hear people go, I'll go and turn it on and we'll come back in 15 minutes time because it'll be stable, because it'll be all over the place. Stability of solid state electronics these days is pretty reasonable. So, but you need to know as foundation candidates sensitivity, selectivity, stability. There's more than likely going to be a question which will probably remove one of them and they'll ask you what the missing one is. Now I talked about there's lots of controls on transceivers, on transmitters and receivers. You need to have a bit of an idea about AF gain. No, so this is audio frequency gain. That's your volume control. RF gain. So if we go back a step here, on the RF amplifier, they could have a knob which enables you to increase or decrease the RF gain. So that's an RF gain control. Squelch or mute. Now, this is usually to do with FM. If you don't have a squelch control or a mute control on FM, you get the hash. You get the background noise, and so what we are able to do is introduce the concept of there being, if it's past a certain level, if the signal is not there, it mutes out that background noise, and so it only turns on, if you like, when there's an actual signal there, so it mutes the background noise. Your mode control, your mode switch, which is AM, FM, upper sideband, lower sideband. There can be, on modern transceivers, there's a digital setting. There's a CW, which is your Morse code setting, etc., etc. Your variable frequency oscillator, so that's how you tune. You tune the frequency. And there is a incremental, so there is a little fine tuning when you get to somewhere where you need to be, which is really handy when you've got single sideband, and we'll demonstrate that in the practical. Because if you're not quite on frequency with single sideband, what people say is it sounds like duck talk, and it does. So you need to just tune it in so that's what that incremental tuning enables you to do. A band switch, which enables you to select, and these are all of the frequencies that the foundation license can operate in. So 80 metres, 40 metres, 15, 10, 2 metres and 70 centimetres. And your carrier level, so there is the ability to control the RF oscillator level. Some questions. FM stands for? The device that generates the carrier in the transmitter is the... Now, this may have a block diagram with it missing, with the word missing. Seen that represented in a couple of assessments. If a transmitter is overmodulated, it is likely to... Now, can I just say, it can be any of these. But which one would you select using your exam technique of safety and interference? Cause interference is the one that I... Okay, ability to receive weak signals.